Hello everyone. First thing we're going to do is now start shifting gears to convergent tests. And so these are tests that we can use to determine whether a series will converge or diverge. And the very first one is the nth term for divergence. Sometimes this is called the divergence test. So sometimes I would just call it the divergence test. And this is actually very, very straightforward. This is one of those things where if we're taking the limit of our function, it has to equal 0 just for the possibility that it may converge. So if the limit does not equal 0 as you approach infinity, it's always going to diverge. So for this particular test, it's not going to confirm whether a function converges, but it can definitely tell you if a series will diverge. And so in this case here, the limit doesn't equal 0, it diverges. But if the limit does equal 0, then we can still converge or we still may diverge. So for the bottom examples here, we're just going to look at them and see what we can determine if something's going to definitely diverge or not, and then maybe converge, we're not sure. For some of these questions, we can actually determine whether or not it's going to converge based on what we've learned already in the previous videos. So for example number 1, we're going to look at this problem and we're going to see that the limit as n approaches infinity squared minus 3 over 2n squared plus n. Well, we can see that since the highest degree in our numerator is equal to the highest degree in our denominator, then this limit is actually equal to the leading coefficients in front of those terms. So this limit is actually equal to 1/2. Therefore, I know that this series actually is going to diverge. I know that for a fact. So I don't have to do any tests on it. It's going to diverge, and we can move on from that. For example, number 2, I know that the limit of this function as n approaches infinity of 2 over n is equal to 0. So you were thinking, okay, this can converge or diverge. But in a previous video that we've now done, we can see that this can be rewritten, this function can be rewritten, pulling the 2 out as we go to 1 over n, and we know that this is a harmonic series. That's hard to see, but it's a harmonic series, and we know that harmonic series is actually going to diverge. So even though this limit tells us that we may converge, we know that this is a harmonic series, therefore it's going to diverge. For example number 3, we're going to look at the fact that the limit as n approaches infinity of cosine of n pi actually doesn't even work. There's no limit for this because we're going to go back and forth. We're going to oscillate between -1 and 1. So since the limit doesn't exist, I automatically know that this is going to diverge because it doesn't pass the nth series test. So right now we have 3 divergence, one where the limit doesn't exist, one where the limit does, and then one where even though the limit is equal to 0, we still can see that that's a harmonic series. So we're good there. So example number 4, we can look at this and we would be thinking, well, this may be a really hard limit to see without actually breaking this apart. But what we could do here is we can say that this is rewritten, you can rewrite this as 1/2 to the n times 1/2. And so I can rewrite this one more time as 1/2 sigma infinity as n equals 1, n equals 1 of 1 over 2 to the n power. You're thinking, well, maybe this is really hard to see, but it's really not, because this is just 1 over n, 2 over n. Well, this is actually a bottom-heavy function, so a bottom-heavy function will obviously go to 0. So our limit for this function will actually equal 0. We can go one step further with this question, and we actually know that this is actually a geometric series because we can see that we have some r raised to some power n, and so our r is going to be less than 1/2. Therefore, we know that this series is definitely going to converge. And there's a video on that as well for you to see. So we know that. We can actually find the sum of this series as well if we want to. And then, for example, number 5, students will think, oh yeah, this is like pretty easy to do, but if you look at the limit as n approaches infinity of 2, well, remember the limit as n approaches anything, it doesn't matter what this is, of a number is still that number. So we're looking at the graph for y equals 2, and so it's always going to go to 2, it's not going to be 0, so we know that this does not pass the nth term test or the divergence test, so this is going to also diverge. All right. And then lastly, we can look at example number 6 and see what we can do with this. And there's 2 ways we can look at this problem. The first one is that the limit as n approaches infinity of 4 to the n over 3 to the n. Well, this is a top-heavy function, so this limit is going to go to positive infinity or does not exist. So we know that this series is actually going to diverge. Another way that we could look at this problem is we could realize that this is also a geometric series. And we can see that our r in this value is actually greater than 1. Therefore, it's also going to diverge. We had a video on that as well. So that's our little examples of our nth test divergence. And so, like I said before, the most important thing here is just to see if the limit does not equal 0. If the limit does not equal 0, you're guaranteed that it's going to diverge. And we've seen a couple of examples where the limit will equal 0 and there'll be some converging or diverging. So these particular examples, we actually knew what we did based on videos we've talked about before, concepts we talked about before. So I hope that helps, and I will see you guys in the next video.